So in this video we'll be talking about permutations and combinations again. Permutations, just a reminder, are when we're really concerned about the orderings of things, and so situations in which order actually matters. Combinations, on the other hand, are really just the collection of things in which order really doesn't matter all of that much. So some examples of permutations might be whenever a group is trying to select a president, a vice president, and a secretary or something like that. Another example might be when we're talking about finishers in a particular race, or when we're talking about phone numbers. So the order of the digits in a phone number definitely matters. Combinations, on the other hand, examples of those is when we're talking about hands of cards that you have. That doesn't really matter in which order the cards are really dealt. All that really matters is what cards end up in the hand once all of the dealing is done. Another example might be whenever we're talking about committees of people. So we're not really having any particular person in any position on the committee. You're just on the committee, and so their order in which you were put on the committee doesn't matter at all. We're just worried about how many people are, or which people are on the committee. So one thing to, again, kind of recall is that when we were looking for the number of arrangements of two letters from a collection of 5 letters, we started with all possible arrangements of those letters, and then we grouped the arrangements together based on whether or not the first 2 letters were exactly the same. And so what you're seeing here is the all possible arrangements of the letters A, B, C, D, and E, so the first 5 letters, and we grouped them based on whether or not the first 2 letters were going to be the same. So the first group, we have A followed by B, A followed by B. We have 6 of those. In the second group, we have B followed by A, B followed by A. We have 6 of those, and so on and so on. And so in each one of those groups, we had a total of 6 possible arrangements that we could group together in one group depending on what the first 2 letters were. And so what this did was allow us to come up with a formula for computing those number of permutations. So the permutations where the order mattered. And this gave us a formula something like the 5 permutation 2, where we had 5 factorial divided by 5 minus 2 factorial. The 5 minus 2 gives us a 3 factorial in the denominator. So where did that formula really come from? Well, we were looking at the first 2 letters that we cared about, the last 3 letters that we didn't care about, and we had a total of 3 factorial, or 6 different arrangements of the groupings of letters that we did not care about. And so that was going to give us the number of things in our groups. And so if we had a total number of things divided by the number of things in a group, that's going to tell us how many groups that we actually had. And so the 5 permutation 2 gives us 5 factorial over 3 factorial, or just 20 groups with 6 arrangements in each particular group. And so now, kind of taking that one step further, if we're looking for the number of combinations, so the number of 2 letters from 5 where order doesn't necessarily matter, then we can really think of grouping our groups together based on whether or not the first 2 letters are just different rearrangements of exactly the same letters. So we took all of our possible arrangements, we grouped them into we put them into groups based on whether or not the first 2 letters were exactly the same, and now we're going to take those groups and put them into larger groups based on whether the first 2 letters are just rearrangements of the same 2 letters. And so what we have in that particular situation, so then our smaller group where the first 2 letters were A, B, then we put that together with the group where the first 2 letters were B and A. Likewise, if we look at the group where we had the first two letters were AC, then we put that into the larger group where we had the letters CA. And if we do that, what we find is that we've got two of our bigger groups in with the even bigger groups. And so what we had when we group our groups together, we get two of our 6-member groups in each larger group, and this is really coming from the 2 factorial or 2 possible arrangements of our first 2 letters in each group. And so what that gives us is the number of combinations of 2 letters from 5 letters is going to be our 5p2 divided by 2 factorial. So we're taking our number of groups, we're putting those into groups of 2 each, and so how many do we have left over? That's going to give us 5 factorial divided by 2 factorial times 3 factorial, and in this, we'll change up our notation a little bit, and since we're talking about combinations instead of permutations, we would really have 5 choose 2 being 5 factorial over 2 factorial, 3 factorial, which gives us 5 times 4 on top, a 2 on the bottom, and so we have a total of 10 different ways of choosing 2 letters from 5. And so in general, if we wanted a formula for choosing k things from a collection of n things, then that formula is really given by this nck, where the numerator is going to be n factorial, and in the denominator we've got the product of k factorial and n minus k factorial. Now that's the formula, but really most of the time we're probably just going to use our calculators to calculate those numbers rather than really trying to calculate them by hand. So let's look at an example. Suppose we want to compute 6 choose 4. And so we want to choose 4 things from a group of 6 things. And we want to check this answer by finding all of the ways of choosing the 4 letters, choosing 4 letters from the letters A, B, C, D, E, and F. Okay. So the solution for that is really just applying the formula. So 6 choose 4, we've got a 6 factorial on the top, a 4 factorial in the denominator, and a 6 minus 4 factorial in the denominator. So we've got a 6 factorial divided by a 4 factorial times a 2 factorial, which if we did just write all of those numbers out, we can cancel our 4s, our 3s, our 2s, and our 1s, leaving us with 6 times 5 on top, a 2 on the bottom. 6 times 5 gives us 30 over 2, or 15 different ways of choosing 4 letters from the 6. So now, since the letters we kind of imagine them as being in this alphabetical order, A is less than B, is less than C, is less than D, is less than E, is less than F, then we can start off choosing the smallest letter in each group, and we only want to add in any larger letters that we happen to have. So if we start off with the smallest letter in each grouping being A, or the smallest letter being B, or the smallest letter being C, or D, or E, or F, then if we want to throw in another letter, we're only allowed to throw in a larger letter. So from A, we could have a B, a C, a D, a E, a F. From B, we could have B, C, B, D, B, E, B, F. C, we could have C, D, C, E, C, F. D for D, E, and D, F. And for E, we can just pretty much just throw in only the letter F. That's going to be bigger than E. Now, if we kind of think of at the next stage, we just want to throw in only another larger letter from the letters that we've already got. Well, our possibility AB we could throw in ABC, we could throw in D to get ABD, we could throw in ABE, ABF, and so on. And so those are the possibilities for throwing in an extra letter with our group AB. Same thing for CD, we could throw in D or E or F. For AD, we can only throw in E or F. For BC, for example, we can only throw in D, E, and F. And even for some things, it's not even possible to really extend because we don't have any larger letters. And so, for example, if we chose D and F, well, there's no letters larger than F, so we can't extend that one. For E and F, there's no letters bigger than F, so we can't extend that one either. And so we can kind of use this ordering as a way of getting these systematic arrangements so that for our possibilities we have A, B, C, D, A, B, C, E, A, B, C, F, A, B, D, E, A, B, D, F, A, B, E, F, A, C, D, E, A, C, D, F, A, C, E, F, and so on and so on. And if we kind of keep going with that, we see that the smallest letter that we can have and still throw in 3 other letters is just going to be C. Or the biggest letter that we can throw in and still be able to throw in 3 other letters, and beyond that will just be C, D, E, and F. And so this way we do have a systematic listing of our total of 15 different possibilities. All right, so now let's look at a few problems in this situation. So an example problem might be that a sandwich shop has the following possibilities for toppings. They've got spinach, cucumbers, onions, peppers, lettuce, tomatoes, olives, and pickles. And a couple of questions that we can ask are, how many ways can you make a sandwich with exactly 3 toppings? Kind of following that up, how many ways can you make a sandwich with at most 4 toppings? And so our solution with that, well, in sandwiches with only 3 toppings, now we also introduce another similar notation for our choosing, that it kind of looks like a fraction, except we don't have a fraction bar. We have these 2 parentheses, we've got an 8 on top, we've got a 3 on the bottom, but we do not have a fraction bar. And so that's our notation for something that we'll call a binomial coefficient, and we'll use that. That will show up later in probably the next section. But that's another common notation that you see used for making these combinations. So 8, choose 3. We want to choose 3 things from 8, and so plugging that into our calculator gives us a value of 56 different sandwiches with 3 toppings. Now for the second question, how many sandwiches with at most 4 toppings? Well, our options for that, at most 4, we could have 1 topping, 2 toppings, 3 toppings, or 4 toppings. And the number of ways that we can have 1 topping is just going to be 8 of the possible, and we're going to choose 1. For the 2 toppings, 8 possible, and we're going to choose 2. For 3 toppings, 8 possible, and we're choosing 3. For 4 toppings, 8 possible, and we're choosing 4. And for our total number with at most 4, we're just going to add together all of those possibilities. And so again, using our calculator to compute these combinations, we end up with 8 choose 1 is 8, 8 choose 2 is 28, 8 choose 3 is going to give us 56 like we had before, and 8 choose 4 is going to give us 70. So if we add those together, 8, 28, 56, and 70 gives us a total of 162 sandwiches in which we can have at most 4 toppings. And so another example, suppose that we have a group of 12 friends and they wish to divide themselves into 2 teams of 5 people, and the last 2 people remaining will be left as referees. The question is, how many ways can this be done? And so the solution for this one, that suppose we want to choose the first team, well, we've got a total of 12 people and we want to choose 5 of them. So 12 choose 5, plugging that into the calculator gives us 792 ways. So now then, having selected those first 5 5 team members, that's going to leave us with 7 people left over for the second team. And so how many ways can we choose another 5 people from the 7 people left over? Well, 7 choose 5 gives us 21 different ways of choosing that second team. Okay. Now, choosing the first team, then choosing the second team is kind of like performing 2 different experiments, one followed by another. And so the fundamental counting principle says that we will take the number of ways to do the first team and multiply that by the number of ways to choose the second team. So we have 12 choose 5 times 7 choose 5, or 792 times 21, giving us a grand total of 16,632 ways that the 12 friends can divide up into 2 teams of 5. So kind of another example might be, how many ways is it going to be possible to get a full house from a standard deck of 52 cards? Now, for what exactly is a full house? Well, a full house is where we have 2 of one rank of a card and 3 of another rank of a card. And so we're being dealt a 5-card hand, and we want to know how many ways is it possible to get a full house. So kind of one example of a full house might be if somebody dealt us a 2 of hearts, a 2 of diamonds, so that's our pair, and then our 3 of a kind might be 3 of hearts, 3 of clubs, and 3 of diamonds. And so how would we calculate the number of ways that we can do this? Well, the number of ways of choosing the pair, well, first of all, we have to choose the rank. So we've got 13 different ranks of cards, so ace, 2, 3, 4, all the way up to kings. So we've got 13 different ranks, and we want to choose one of those. And then for each rank, we've got 4 possible suits, so we want to multiply that by 4 choose 2. So we want to choose the rank, that's 13 choose 1, times the number of ways of choosing the pair, which is our 4 choose 2. Then we can do the same thing for the 3 of a kind. Well, we don't want to choose the rank from the pair, so we have 12 different ranks that we can choose from. So 12 choose 1 chooses the rank of the 3 of a kind, and then of the 4 different suits, we have 4 choose 3, which is our number of ways of choosing the 3 of a kind from the 4 possible suits that we have. And so we multiply all of those. And so our total number of full houses is just going to be 13 choose 1 times 4 choose 2 times 12 choose 1 times 4 choose 3, or 13 times 6 times 12 times 4, giving us a grand total of 3,744 ways in which we can be dealt a full house. So kind of another example along those same lines, we could ask, how many ways is it possible to get 2 pair from a standard deck of 52 cards? Again, assuming that we're being dealt a 5-card hand. And so an example of something that might be 2 pair, suppose someone deals us the first pair, we get the 2 of hearts and the 2 of diamonds. For the second pair, maybe we get the 3 of diamonds and the 3 of clubs, and then we get some other kind of random card that doesn't match any of the other 2, so we get maybe the 5 of diamonds. Might be an example of a hand where we have 2 pair. And so how do we calculate how many of those are possible? Well, in kind of a similar way, if we want to choose the first pair, well, we've got 13 different ranks, and we want to choose one of those ranks, so that's 13 choose 1. Now, once we pick the rank, we have to choose 2 of the cards from the 4 different possible suits for that rank, so that's going to be 4 choose 2. So just choosing the first pair, we have 13 choose 1 times 4 choose 2. We can do the same thing for the second pair. We have 12 choose 1 because we want a different rank. So we've got 12 possible ranks that are different than the one that we chose for the first pair. Then we want to choose 2 cards from the 4 possible suits. So that's 4 choose 2. And so for the second pair, we have 12 choose 1 times 4 choose 2. And then finally, for the last card, we don't want it to match any of the other ranks that we already have, because then we might end up with a full house. So we've got 11 possible ranks that we can choose from, and we want to choose one of those. And from those 4 possible suits, we've got 4 choose 1, because we're only taking one possible card. And again, the fundamental counting principle says that for each one of those events, we're going to multiply those together to get a product. And so our number of possible ways of getting 2 pair is just going to be 13 choose 1 times 4 choose 2 times 12 choose 1 times 4 choose 2 times 11 choose 1 times 4 choose 1. Which gives us 13 times 6 times 12 times 6 times 11 times 4, for a grand total of 247,104 ways in which we can be dealt 2 pair. So I hope that this has been kind of insightful in that kind of real concrete examples of where we would use these combinations to count real-world problems. And so I hope you've enjoyed this, and I will see you guys next time.